Okay, so I'm Vaishnav. So I'm here to talk to you about. So some of you might have attended the previous talk on the other room on the MSPM Suro. So some of the smallest devices. Here we are discussing the other side of the world. Is it even relevant to run Zephyr on some of the largest cores out there? So, and the alternative there is real-time Linux. So we are doing a comparison of what works best in Zephyr, what works best in real-time Linux, and you are a system integrator, you want to choose between two, and or even today, is Zephyr ready for a competition with real-time Linux? So I work with the software team at Texas Instruments. So we work on multiple open source projects. Zephyr RTOS is one of them. I've been working with Zephyr RTOS for the last 5 years. I'm the maintainer for some of the Zephyr RTOS upstream platforms for TI. So this is the overview. We'll have a look at what this class of processor, or maybe we'll start from something more fundamental, like what is real-time, then move on to how Zephyr does it, real-time Linux does it, and a comparison between them. Okay, so what's a real-time system? So, for example, you are viewing a video on your YouTube and it's playing smoothly. Do you think that's a real-time system? How many of you think that's a real-time system? Okay. Even though, so a hard real-time system means that from the start of the event to the response, there should be a determinist latency. So in case of your YouTube videos playing smoothly, you have buffering mechanisms where your frames are preloaded and it's playing smoothly. But think of it in a different scenario. You are doing a video call with someone. There is no way to have a buffering mechanism. So you have to have, so that's example of something where you need some real-time response. So that's a very simplified explanation of something like a high performance system. So you are viewing video on 4K without any lag or glitches, but that does not mean your system is real-time. So this is kind of a textbook definition of your real-time system. That means the latency or the response time for a particular event, it's not just the correctness of performing that action. So you have to perform that particular action. The system needs to perform it within a particular latency restrictions, and the worst case of that should be better than your system response should have some for example, you are responding to some sensor data on a robot and you take actions based on the sensor data. So you will have some round trip latency for the sensor data incoming to the taking an action on an actuator or something. So if you miss that, your system is gone. So it can lead to a system crash. That's the meaning of your system being a real-time system. Now there is a misconception that throughput or performance is real-time. So you cannot say that. So for example, you have something like Ethernet or something where you have 10 Gbps of bandwidth, but that does not mean that your packet-to-packet latency or the time for you to take response to a particular event is optimized. For example, if you have played online video games, you will be worried about something called ping. Even though you will have a high bandwidth 1 Gbps connection, but if your ping is bad, your response on that video game is going to be bad. It's a similar concept. Then another thing is that you maybe if you have has any of you worked on real-time Linux before? So real-time Linux is kind of right now it's the same source code base, and it's you can think of it as a variant of Linux which has few modifications and configs to have this kind of deterministic performance. And a misconception is that you enable something like config preempt RT equal to Y and you get a real-time system. So that's not true. It just makes some subsystems or the core part of your kernel real-time. So in your system, starting from your hardware to the kernel to your user space application, everything needs to be tuned for your real-time or deterministic performance. you mess up something in that real-time path, you will lose that deterministic response. For example, your interrupt controller, the hardware is not firing the interrupt latencies in a deterministic manner. In that case, even if you do all the optimizations in your software, you are never going to achieve a real-time system. Same thing with your memory subsystem. If your memory subsystem cannot provide something like a worst-case latency that's lesser than your system's acceptable latency, then you can never tune. You enable your system with a real-time kernel, and then you cannot achieve something with a something like a real-time system. Now let's look at the application process. So most of the Zephyr support today is in the MCU class of devices, and that too widely in the connectivity or the networking areas. And if you look at there are also application process supported. So these are processors generally designed to run high-level OS like Linux or QNX, and they are used in different areas. So sometimes you will use some Raspberry Pis for your file servers or things like that. Some of these goes to automotive cars, some of these goes to robots and different use cases. So what differentiates these from the generic MCU platforms in Zephyr is that it usually has a memory management unit. Then the interrupt controllers and hierarchy, it's slightly more complex than something like, if you take an M-class devices, it usually has something like an NVIC. It's a similar interrupt controller compared to something like a gig interrupt controller that's seen in this ARM application processors. Then it usually has multiple levels of cache hierarchy. Then usually these have multiple cores. So these are usually designed to run workloads rather than be in a real-time feedback loop. So they have multiple cores to distribute the workload, and it can run in SMP mode. And they don't usually run out of internal SRAM or flash. It usually runs out of DDR. And they are designed to run an OS like Linux. So why would you even bother to run something lighter like Zephyr RTOS on such kind of platforms? So on the right, that's a snapshot I took from. So if you have looked at Zephyr supported boards, so you have some nice filtering mechanisms where you can filter by architecture, some SoC vendors and all. So this just a subset of the application core platforms. So all are I filtered by ARM64. There are x86 platforms. There is ARM 32-bit ARM platforms. So there are different application processor platforms that's already supported it. And if you look at it, so there is core support for memory management, the MMU, then the interrupt controller, all support is there. And you even have references of running this. So you run the Zephyr directly on top of the hardware. That's your maybe the normal way of using. Sometimes you might run Linux and Zephyr in parallel using an hypervisor, and even there are references for that. So if you look at the third line, there is a virtual machine example. So you can run Zephyr on top of a hypervisor. And one key feature that we discuss along this, by the architecture of how this RTOS is designed, it can offer extremely fast boot up time compared to Linux. So Linux, by the architecture, you cannot have that much boot up time. So you can trim, tune, and customize and achieve to some level of fast boot up. But by design, there are few things that Linux does as startup that Zephyr can do at compile time. So it becomes much faster, your application boot time. So then the main thing is Zephyr conforms to different standards of this POSIX compliance. So have any of you heard about this POSIX? So it's a standard that helps you to have applications portable across multiple OSs. So if you would have worked with QNX or something like that's also POSIX compliant. So you will have some lot of Linux applications that work directly on those OSs. So you can do the same thing in Zephyr as well. Then the device level model, and the other thing is real-time Linux evolved from the generic Linux to become a real-time Linux distribution. But Zephyr, from the start itself, you are developing a device driver for Zephyr. So you have the mindset that you are writing a device driver for an RTOS, and you are supposed, you will be following that kind of development practices. But in Linux, you might be following something like a performance-driven mindset, where your deterministic reaction of that device driver, you may not care that much. We'll do a case study on why that's important and why that's complex in Linux as well. So this is the POSIX compliance. So POSIX compliance, so there are different levels of compliance. So what it essentially means is you will need to make some changes in the build systems and all, but without a lot of changes in your application code, you can directly run an application that works on Linux to Zephyr. And there are already examples in the tree, some things like Civet Web, that's an HTTP server example. You can run on your Linux, you can run the same application on having your Zephyr also as a host. And people have ported different benchmarks, something like CoreMark Pro and all directly. So you don't change a lot of parts of your source code, but you will need to change the build system. So you may need to build it specifically. So it's not a binary compatible thing. So it's a source compatibility between multiple OSs. So what it gives you is you can use a lot of applications that you already work with on Linux, so file system application, all will directly work on Zephyr as well through this POSIX layer. So the next thing is the device driver model. So Zephyr has a good device driver model where, so if you have written device drivers in Zephyr, you would have seen and are familiar with the device driver model. I'm not planning to go deep into that. But what the device driver model along with the device tree in Zephyr gives you is that you can have the same device driver. So let's say you have one, almost every semiconductor manufacturer will reuse their IP across their devices. So you have a IP that's integrated in different manners. So you have different ways of clock or power being integrated. You have reset being integrated, or interrupt is different for different platforms. You can have the same device tree, so you can have the same device driver, and that's by the mechanism of the device driver model and the device tree in Zephyr, where you have your platform specific things or SoC specific things decoupled from your driver logic. And you can have the same driver work on a system with an MMU or a simple microcontroller without an MMU as well. So if you look at this device, these are two tier devices that I took for comparison, and these are devices that has support in tree as well. Lot of IPs are being shared, so you don't need to do different development for these device drivers for these platforms. And this platform has an application processor and an microcontroller, so it's a heterogeneous multi-core system, and you don't need to write device drivers for different of them. So independent. So that's the abstraction that Zephyr provides. So with if you are a semiconductor manufacturer, you with very minimal investment, you can have driver support across different cores on your device, and reusing the same device driver code. Okay, this with basics of how Zephyr does different things. Now let's have a look at real-time Linux. So real-time Linux, it was till last year, it was a patch set that was being carried on top of the normal mainline Linux kernel. It was called the preempt RT patch set. What it does is, so looking back to the definition of this real-time deterministic response, so when an event comes, you have to respond to it as soon as it possible and within that system budget of latency. So for that, what you need to do is everything non-important, you should be able to preempt and take action for the interrupt or event as soon as possible. So that's what the preempt RT patch set is basically doing. So different parts of the kernel, so it's doing so the high resolution timer support, then the threaded interrupt handlers, unless you mark with that flag all interrupt handlers by default becomes threaded interrupt handlers, and even those get preempted. then different sleeping spin locks, and also basically it means that you don't have pieces of code that's holding your system that makes it non-preemptible. So at any state you are able to respond to a higher priority or critical event. That's what the fundamental things are there in the real-time Linux. So today it's not a patch set, today it's part of the mainline kernel. You can enable the configs and you will get support on your platform. But again, we discussed it in the beginning. So you just enable one config, you never get a real-time system. You have to tune it for your system. Yeah.
So when you say we have to tune it for our system, do you mean like actually going and fixing the drivers that may be causing hindrance to the real-time performance?
So driver and all comes at a next level. So maybe if you start with real-time Linux, you will do something called a cyclic test. So that's a standard benchmark that you do. So it measures the, it kind of measures the wake up time or response time. So, and it gives you a plot after running for some time, and you will be able to get your worst case latency. And that depends on your system. So one TI platform and one other SoC vendor platform, it will be different. Even between two different TI platforms, it will be different. It's a function of your core, then your memory subsystem, interrupt controller, all those things. So at that point itself, you will understand, okay, is this hardware even capable of my deadlines? After that, you need to perform tuning at your kernel, and most of the kernel part, it might be done. Then your device drivers. For example, I'll go through one debug where we did for device driver and why Linux is more complex. So these are the tuning knobs. So the things is, so you have to disable a lot of functionality if you are debugging real-time issues. So you cannot have debug or anything. So because you are and then there is scheduling policy, different scheduling policies that allows then even from the tuning starts from your user space application till your kernel device driver, and also at the and a lot of things at the core part of the kernel is already there, but you may need to tune or change. So you maybe something you might do is you will pin your application to particular CPUs and decouple it from the CPU that does the scheduling. So you can do some things like that with isol CPUs. You can set the even IRQ affinities. You can tell the IRQs are being serviced by particular cores alone. So those kind of tunings are what I'm talking about. Then these are at the kernel level, you do all the tuning, but you have a poorly written device driver. But when I say poorly written, it might not be even visible to you that it's poorly written. We'll look at that why. And if that device driver is not meeting your or not written in a way that it's supposed to give deterministic performance, you won't get a system that works on real time. Again, multiple subsystems might interact, and that might cause problems with real time as well. So this was one debug we did in the past, where so this use case was where there was one robot. It was getting this LiDAR data through SPI. So what we were seeing was that when the robot was running, at some points, at random occasions, you will need to not service the data properly from the LiDAR. So you were seeing something like a latency spike. On 99% of the cases, you were servicing the data correctly, but at some point you were seeing latency spikes. And when we debugged that issue, and what found for debugging that, you have to trace from your user space application till your hardware what's happening. So that's so this was how once iMessage goes in Linux. So there's an IOTL, then it goes to your particular device driver, and what we found was in that device driver, it was not really visible, it was poorly written. And this issue only happened when we were working on DMA mode of that SPI operation. Then we found out, okay, what happens in the DMA engine framework and in the particular DMA control driver, what happens, and in the hardware. So in the end, what we found out was that in the DMA engine or the DMA controller driver, there was a deferred task that was giving a completion to the SPI driver. So if you look at just the SPI driver, you will say that, okay, I'm waiting for a completion. But the completion where it comes from in the DMA driver, that was a deferred tasklet or something like a low priority. And if your CPU load is higher, that might get delayed much further. So that was what we were seeing. In some cases, we were seeing that we were missing that deadline. So in the end, we debugged and fixed that device driver. So what I'm trying to say is that, okay, even though your core kernel moved to or has patches to make it preempt RT, it does not mean that you will get real-time support on all your platforms. So you buy one SoC vendor platform, you put config preempt RT equal to I, you never get that system. Even if you go to RT Linux wiki, you will find all the tuning options and how you are supposed to create a real-time system. So that's where it becomes complex. And as a system integrator, you don't want to go and really debug your SoC vendors device drivers. So that's how. So this all originates from the place that you started from a non-real-time Linux system and you are trying to make it real-time. But the device drivers initially were not written with that mindset in mind. But if you have worked with any traditional RTOS, all the device drivers will usually be written in that manner. So this is the last slide. So I have some numbers, but it's not easy to do a fair comparison between Zephyr RTOS. So if I do an application boot time comparison, I can do a hello world in Zephyr RTOS, and even the simplest Linux system is actually very complex to compare to hello world. But I can tell you, maybe look at why the differences is. Like if you are familiar with the device tree architecture in Zephyr, so there is no runtime parsing of device tree in Zephyr. So even though your representation is in device tree sources, it does not get compiled to a DTB and gets parsed during your boot up. It's during the compile time, it's converted into headers, and that's what being used for the information for the device drivers. So there is no, during the boot up, you have all the information to perform the initialization. But in case of Linux, at least for your ARM platform, ARM64 platforms, you have runtime DTB parsing, so you cannot get around with that. And after that only you understand even what kind of platform you are working on. So that's one area where even if you do any kind of optimization, you cannot beat that. The next thing is even the Linux boot time also it differs. So with the kernel startup time, then your init systems, all those tuning. So even if you leave away the init and just the kernel startup, so comparing these differences, Zephyr is likely to perform much better. Even the numbers are better, but you cannot do a direct comparison between a simple Zephyr application with a complex Linux RT Linux system. Then the device drivers. So the device drivers on Linux, it might not be written with a mindset of having deterministic performance. So, but in Zephyr, it's an RTOS. You will usually do that, and that's how you usually write the drivers. Then the Zephyr tuning options, most of the tuning options are picking your scheduler, different priorities for your user space, device drivers, and different things. Everything is in your config files. You can edit it in your menu config, and you have a single interface where you can configure these things. Compared to Linux, where you have to tune different parts so for your user space application, you might be tuning it in a different ways. In the kernel scheduling policies, you might be changing it in a different way. Then your device drivers, you might need to modify. Then looking at areas where Zephyr is lacking, or if Zephyr is so good, why are already not people using Zephyr in these cases? So if you look at the ecosystem, like the networking stacks, different stacks in Linux, that's much more richer than what's there in Zephyr today. So if you ask, okay, are these supported in Zephyr? Is how good are they support? You can't say that it's equivalent to something that's being there in Linux, and that's because there is lesser number of people using it. When more and more actual use cases use it, it might become better. And then the other thing with the real-time Linux is I discussed. So if you want to debug things or if you want to go to production, you might need to remove a lot of features like runtime power management. So which might be interfering with your real-time response or deterministic response of the system. So in Zephyr you don't have that kind of issues in at least in simpler platforms.
But Zephyr as such does not implement runtime.
No,
Yes?
I think yes. Yeah, runtime PM, yes. Yeah.
So like the drivers suspend and resume if they're not idle.
Yes, yes. Drivers have the hooks for that, yeah. Kernel calls that.
We have 10 minutes.
Oh, I'm almost done.
I have one question. So, like, you were told that currently Linux drivers are made in such a way without an RTOS mindset. So, what is the thing that actually is like an RTOS mindset? What is the prognosis with the current driver model? How do we have to handle it? Like, Texas still lost RTOS made in wrong way or what?
Or like how you process the bottom half of or interrupt. So you might be putting it in a deferred tasklet or something, and based on that you are waiting for a completion. So and this is never bound to have a deterministic time for completion. So this might get preempted. So the best ways, or the previous problem how we solved was look at your hardware, see whether you have different mechanisms to have the completion. So here the problem was, okay, we were waiting for that RX DMA was waiting for completion from the DMA driver. So if you look at any spy controller, it typically has an interrupt within itself which could give you the information of some completion. If you had short circuited that path and used that completion directly from the IP, you would have no problem. But if you look at the driver and you are a reviewer, the driver is written not in a really bad way. It's written and it's waiting for completion, but the mechanism for completion was something that could be delayed, and because when the driver was written, maybe the person did not think that okay, this was getting used in a real-time system. Because if you measure all these performance tests and all, you won't find it. So it's the packet to packet latency that's getting worse here. If you look at even with this mechanism, you may see that the spy is working at 40 Mbps. But if you try with the smallest packets, you will see that the packet to packet latency is varying. So and that's where your latency spikes comes in your performance.
You said the DT parsing in Zephyr is compile time, right? So in case of something that's on-demand sensor integration, maybe something like gray bus integration, how does it help in those? Because I think it will be pretty hard for it to...
Even how gray bus is today is it's compile time.
Okay.
When it's running, you cannot change what
Particular sensor.
correct. Or you have to
You have to have reload modules basically.
so how gray bus is implemented is you create a manifest and pass it to your host.
Yeah.
So that manifest creation, you could make it dynamic, but the platform, how it discovers the devices on the platform, it's always static.
Krishna, when Linux is tuned for real-time usage, then where does real-time Linux run? Is it on Cortex-A only or Cortex-R, which is...
It's always on Cortex-A.
Is it because of size or sizing?
Linux typically runs on systems with MMU, so the Cortex-R does not have an MMU, so you usually don't run Linux on the Cortex-R. You usually run an RTOS only on Cortex-R.
Yes. So even in this comparison, it was like Cortex-A only?
Yes, yeah.
Does Cortex-A have determinism in hardware by itself? Like,
So that's a subjective question. So if you look at the MMUs and also your translation latencies could have some worst case bound, but the real-time system does not say that it's the fastest system. It says the latencies are only bounded. So as long as that bound for your worst case performance is larger than what this course provide, this practical usage. And if you look at things, you already see QNX and other real-time OS running on this A course.
For system tuning, you had mentioned about can we consider it for power management as well?
So generally, like that depends on how the power management is implemented. So usually in A course, you might have a call to go to the ARM trusted firmware or something and then come back. So it's the same course. So and that call is not preemptible.
Which one?
You make a PSCI call, it's not preemptible. So you
ATS by nature is a bare metal firmware, so it has no concept of IRQ handling or jumping back to kernel context. If you
So-
are stuck in that EL3 context,
then you could miss your deadline.
And it is also mentioned about task partitioning.
Putting it on different CPUs. Yes.
So then how the scheduling will happen?
So that only tells that so you isolate the CPUs from the scheduler. That means the scheduler is not running will not schedule any other things on that course. So it will only run your particular workloads. Yeah. And you can do the same thing for interrupts as well, setting the interrupt affinities. Yeah. Okay. Thank you everyone. Bye.